Welcome to this video supplement involving solving polynomial inequalities and solving rational inequalities. In this video, we will look at one polynomial and one rational inequality. Our first problem is up on the screen. What we need to do with a polynomial inequality is we need to first get everything on one side of the inequality. In this case, we'll subtract the 2x cubed and the 15x squared from both sides, and then get 0 on the other side of our inequality. Ideally now with polynomials we will look to factor. In this case we notice a greatest common factor of x squared, leaving us with x squared minus 2x minus 15. Now we will factor completely, so this will turn into an x minus 5 and an x plus 3, and all of this is greater than 0. At this stage of the game, we set each factor equal to 0 and notice the key numbers, as we will call them. For x squared to be 0, x would have to be 0. For x minus 5 to equal 0, x would have to equal 5. And for x plus 3 to equal 0, x would have to equal a negative 3. At this point, we go and make a number line. And on our number line, we are going to place any key numbers in order from least, in this case negative 3, to greatest, in this case positive 5. Now as we contemplate this problem, we're going to take each region on the number line and consider how it would work in our inequality. But before doing so, the first thing we notice is that this inequality is a strict inequality. We need values of x that make the expression greater than 0. So numbers that we could plug into the expression and have it actually equal 0 don't work. Hence, on this one we are going to place open dots on each of our key numbers on the number line. Now let's pick a number less than negative 3. For example, x equals negative 10. If we plug in x equals negative 10, x squared would be positive. Square a negative, you get a positive. Negative 10 minus 5 is going to be a negative number. And negative 10 plus 3 would also be a negative number. So everything considered, a positive times a negative in that region will be a positive. Negative times a negative is a positive. Therefore, it is greater than 0, and this region will work, so we'll shade it in. Next, let's come over here and take x equals negative 2, for example. Plug in x equals negative 2, x squared is positive. Negative 2 minus 5 will be a negative number, and negative 2 plus 3 will be a positive number. All considered, in this second region, a negative times a positive is negative. It would not be greater than 0, and that region does not work. Next, let's pick a number between 0 and 5. For example, x equals positive 4. 4 squared is positive. 4 minus 5 is negative, and 4 plus 3 is positive. So in that region, a positive times a negative is going to be negative. It's not greater than 0, so that region would not be shaded in. Lastly, we'll find out how this final region works. Take a number greater than 5. For instance, x equals 10. 10 squared is positive. 10 minus 5 is positive, and 10 plus 3 is also positive. 3 positives multiplied together would be a positive number. That's greater than 0, so our inequality works. We would shade that region in. And now we have our interval notation. Negative infinity to negative 3 with a normal parenthesis, because negative 3 doesn't work, union, parentheses, 5 to infinity. There's our final answer in interval notation. We also have the number line and the factored form. When dealing with polynomial inequalities, this is essentially what we consider. Next, let's look at rational inequalities. The problem we're considering is on the screen. To start us off, the first thing we'll do is subtract 1 from both sides, as we need everything on one side of the inequality and 0 on the other side of the inequality. Now with rational inequalities, we have to build a common denominator. So we're going to multiply each of these expressions by a fraction. For this first expression, for a common denominator, it's missing the x plus 5, so we'll multiply by x plus 5 over x plus 5. For the second expression, it's missing the x minus 2, so we'll multiply by x minus 2 over x minus 2. And this final expression is missing both the x plus 5 and the x minus 2. So we'll multiply by both x plus 5 over x plus 5 and x minus 2 over x minus 2. Now this is just going to be a big fraction, so we'll just write the denominator once in the big fraction, and that denominator is x minus 2 times x plus 5. The whole fraction has to be less than or equal to 0, and now let's figure out the numerator. Keep in mind we have to distribute, so we'll have 3x plus 15 plus x squared minus 2x minus, now let's subtract the entire quantity when we FOIL out these terms here on the screen. We would have x squared minus 2x plus 5x minus 10. So as we continue to simplify our numerator, from the terms on the left it looks like we have x squared plus x plus 15. Then if we go through and simplify in our parentheses, we have x squared plus 3x minus 10. We have to distribute our negative and combine the like terms, keeping in mind that this whole fraction has to be less than or equal to 0 when we're done. So in our numerator, we have x squared plus x plus 15 minus x squared minus 3x plus 10 all over x minus 2 times x plus 5. Combining like terms, look at this here. The x squareds cancel up in the numerator. X minus 3x would be a negative 2x. And 15 plus 10 would be plus 25. Our denominator is still x minus 2 times x plus 5. And we're looking for where this is all less than or equal to 0. So now, the other thing that I would encourage us to do is to factor out our negative up in the numerator. So we'll have a negative times the quantity 2x minus 25, be careful when we factor out that negative, all over x minus 2 times x plus 5 is less than or equal to 0. Now identifying our key numbers. In the denominator we have 2 and negative 5. Up in the numerator, for 2x minus 25 to equal 0, 2x is equal to 25, or x would be 25 halves. We will place each of those three key numbers on a number line in order from least to greatest. So we'll have a negative 5, a positive 2, and a positive 25 halves. Now notice our inequality has to be less than or equal to 0. It is allowed to equal 0. So the value of x that we plug in that makes the numerator 0 can work. 0 divided by some other number is just equal to 0, and that would satisfy our inequality. However, if we have a 0 in the denominator, that would be dividing by 0, which we can't do, so each of those denominator key numbers turns into an open dot on our number line. And now we'll consider each region one at a time. So for the far left region, plug in a value of x less than negative 5, let's say negative 10. First of all, notice that this negative remains out front regardless of the value of x. Then, negative 20 minus 25 would be a negative. Negative 10 minus 2 would be a negative. And negative 10 plus 5 would be a negative. So that entire region is going to turn out to be positive. A negative times a negative times a negative times a negative is positive. If it's positive, it's not less than or equal to 0, so that region doesn't work. Moving on to our next region, let's plug in x equals 0. The negative sign will be there regardless. 0 minus 25 is negative, 0 minus 2 is negative, and 0 plus 5 is positive. A negative times a negative times a negative times a positive would be negative. That region would be less than or equal to 0, so we shade it in. Next up, we'll plug in a number between 2 and 25 halves. Let's just say x equals 3. We'll have the negative. 6 minus 25 would be a negative. 3 minus 2 is a positive, and 3 plus 5 is a positive. A negative times a negative times a positive is positive. That region would not be less than or equal to 0, so it's not shaded in. Finally, let's take a value of x bigger than 25 halves, which is about 12.5. So let's say x equals 20. If x equals 20, we'll have a negative. 40 minus 25 would be positive. 20 minus 2 would be positive, and 20 plus 5 would be positive. A negative times a positive times a positive times a positive, that would all be negative, which is less than or equal to 0, so we will shade in that region. Finally, for interval notation, the solution on this one would be negative 5 to 2, both with rounded parentheses, union, rectangular parentheses, 25 halves to infinity. So rational functions are very similar to polynomial functions when handling inequalities. The key thing is, remember, denominator key numbers are always going to be open dots. The numerator, we will have to look at whether it's a strict inequality or whether we're allowed to have the or equal to option. Finally, the last item to keep in mind, worth noting, is whenever we're looking at a key number, the only sign that really could change is the one where that key number comes from. So for instance, if we're looking at 2 on the number line, the only sign that could possibly change would be the sign corresponding to our x minus 2 factor. And notice that sign did change, all of the others remained the same. We see something similar over here when we look at 25 halves. 25 halves corresponded to our factor 2x minus 25, and notice that the only sign that changed to go from the region here to the region to the right of 25 halves was the sign corresponding to 2x minus 25. That's a nice way to double check your signs as you move through the problem and to overall check your answer on the number line and in interval notation.